So Bonferroni's inequality is a very practical and very important inequality in probability. What's really nice about it is that it puts together the set theory, the union bound, and then it also puts together De Morgan's laws, if you're familiar with them. And it has very practical usages in statistics. So I thought maybe I could give you an explanation that's very simple to understand. And yeah, so here we go. So we're going to start with a very simple case where we are only considering only two events, and then we're going to expand it to include multiple events. So the inequality states that for any two events A1 and A2, we're going to prove that the probability of their intersection is greater or equal to the probability of each event minus 1. So I'm going to first give the intuitive approach to this question. The intuitive approach is this. So like, let's say we have this is our sample space, and then this is event A1, and then this is event A2. This is like, normally this is what you're used to. So like, of course, you know that's the intersection. But it can also be the case that instead of having such a very like a distributed, the sample space is very well distributed between the two events, you could have that maybe event A is, let me use a different kind of a marker. Event A could be that maybe this is event A, and maybe this is event B. You could find that event B is something like this. So in this sort of case, you will find that the probability of A intersection B, which will A intersection A2, which will be this one here, will be so big. What does that mean? That means that the probability, this is let's say this is A1, and then this is A2, and then this is their intersection. You find that this one will be so large it's approximately 1, and then this one is also so large it's also approximately 1, that when you add them up, this will be 2 minus 1. So the maximum, of course, they can be is 1. So like that's basically what this inequality is going to prove, that when you have these two events, when they are so big, basically the intersection will be at least bigger than this one here. Like, I mean, let's say if this was something like 0.9, this is 0.9, and then if you the total will be like 1.8 minus 1, that will be 0.8, right? That's like this here. I mean, it's pretty big. And then you find like so anyway, let me go to the section to prove this out, to show it clearly. Okay, so we are going to use De Morgan's laws to prove this, and we are going to say that the probability of A1 union A2 complement is going to be equal to the probability of A1 complement intersection A2 also complement. So from there, we're going to show that this one here is the same as 1 minus the probability of A union A1 union A2 is going to be equal to this one is going to, okay, no, actually we're not going to use that. We're going to say that this union here is going to be equal to okay, sorry. Fast pause. All right, so actually with De Morgan's laws, what you're going to instead use, we're going to use the probability of we're going to say probability of A1 intersection A2, but the complement is going to be equal to the probability of A1 union A2 the complement going outside. Sorry, this actually goes here. So that means, but we know that if you have like a union of two events, the probability of A1 complement union A2 complement is going to be equal to probability of, actually it's not going to be equal to, it's going to be less than or equal to A1 complement plus the probability of A2 complement. So that's where the inequality comes from. That means this is equal to this. So that is the probability of A1 intersection A2 complement being equal to the probability of A1 complement plus the probability of A2 complement. Not equal to, sorry, it's less or equal to. So this we know is the same as 1 minus the probability of A1 intersection A2, right? Less or equal to the probability. So this is same as 1 minus the probability of A1 plus the probability, also 1 minus, sorry about that, 1 minus the probability of A2. So you will notice that this one here could cancel out with any of those ones, and then we multiply through by -1 and it will change the inequality. So that will make it probability of A1 intersection A2. This will turn, and then you'll have, this will become positive probability of A1 plus the probability of A2. And then this, one of these ones was cancelled out and this one became negative. And then we have this inequality. But then we can actually extend this to make the Bonferroni inequality, which involves events until n, not just two events A1 and A2. And the Bonferroni inequality says that the probability of A1 intersection AN is greater or equal to the probability of A1 plus the probability of AN minus n minus 1. This is what we're going to prove now. You can pause. So now we're going to prove this fact when you're involving more than two events. So in that case, we're going to still use De Morgan's laws. We want to have the intersection of all these events. We're going to start by the complement. So we're going to start the probability of A1 intersection till AN. The complement is, this complement here is the same as the probability of A1 union AN, the complement of that event. So this one here, with the same logic, is less or equal to the probability of A1 plus the probability plus so many probability of AN. Like, actually, sorry, this is actually a complement on it. So this complement, that so many events on that, so many complements on each. So by the same procedure, this one is 1 minus the probability of A1, the intersection AN, is complement, less or equal to. So now you will notice that each of these is going to have something like, 1 minus the probability of A1, each of those. So each of these ones is going to occur n times. So that means I'm going to have an n minus the probability of A1 plus the probability of AN. So I'm going to have something like that. So the next thing I'm going to, actually this was 1 minus probability of that complement. So next thing I'm going to do is, of course, I'm going to multiply through by -1. I will have something like the probability of A1 intersection AN change of the inequality. So it's going to be a negative. It's also going to become positive. That is A1 then plus the probability of AN, and then this n became a negative n, and then this one became a negative when you multiply it by like -1, but then when you push the side, push this side, because we multiply it by -1, it becomes -1, right? Bring it this side, becomes positive, and that really is the same thing as the probability of A1 plus the probability of AN minus n minus 1. Take out the negative, and that's it. Yeah. You may be wondering, how is this applied practically in real life? And I think that's very important for retaining knowledge. So the Bonferroni inequality is multiplied when you're doing multiple hypothesis testing, and this is really this comes up so often when you're testing, let's say running very many hypotheses. You're trying to figure out of the 20,000 genes, which one is probably like significant to causing a certain disease or whatever. Like it really shows up a lot in genomic tests, because let's say you're running a test on like 20,000 genes, right? So like if you're running your test at a level of alpha, let's say your level of alpha, significant level of alpha, maybe let's say it's 5%, and you're running like, I don't know, 20,000 hypothesis tests, you are probably going to, this number is going to be multiplied like by a lot. I mean, you're going to have let's say you're probably having like 20,000 genes, and there's a 5% significance level. Like basically for the first test there will be a 5% chance of a type 1 error, and then for the next one another 5%, and all of these are going to accumulate and you're going to increase your error of a type 1 error. That type 1 error, if you're probably not familiar with it, is the probability of rejecting the null hypothesis, when the probability of falsely rejecting the null hypothesis, you're going to end up with like false discoveries. So basically the Bonferroni inequality, what it does is, instead of running it at like a level alpha, you're going to run it, let's say if you're running m tests simultaneously, you can divide this level by m. So by m, let's say if it's like 100 tests, that would be like 5% divided by 100. But now, like, I mean, this is like, if this is 5% divided by 100, let's say a 0.05, and then divide by 100, you're gonna have something like 0.0005. This, okay, I mean, theoretically it's applied for that really, but then in some applications this Bonferroni inequality is a little bit too conservative, that you will never make any discovery if you're going to be so strict as to have such a very low level. But like the mathematical bit of it is that you're going to have alpha out of m for the first test, next is alpha out of m for the second test. So for all those tests, the total level of the total probability of type 1 error is not going to exceed alpha. That's how the Bonferroni inequality is applied.